Section 4.4, Evaluating Linear Models. Okay, we've got some words of caution to go over first. First of all, don't fit linear models to nonlinear associations. This is why in the past section we keep saying, always look at the scatter plot first. Make sure it actually looks like a linear association before you calculate the regression and before you calculate an R value. If it's not linear, then these things don't mean anything to us. So we've already checked this one off of our list. Correlation is not causation. I think we have beat that one to death. Yes, we know that. We have to be sure that we don't accidentally say something causes something else just because they're closely correlated. Okay, these next two we have not talked about yet, so that's what we're discussing in this video. Beware of outliers and the effect that they might have on your regression. And also don't extrapolate. Now, we don't know what extrapolate means yet, but we're going to learn why we shouldn't do it right now. Okay, so here we have an example about outliers. So these, both of these two scatter plots show basically the same information, but they look very different. So this first graph over here, graph A, has a point plotted for every one of the 50 states and also the District of Columbia. And it's comparing the population density against the crime rates. So these are the 50 states. And this is the District of Columbia out here. The District of Columbia is extremely densely populated and also has an extremely high crime rate. It does not fit the rest of the data that's lumped over here. So it's certainly an outlier, and it's pulling the regression equation up with it, basically. This equation that's modeling it, the line, has to come up all the way over to it to catch it. Notice the R value that goes along with that equation is a 0.412, so it's not a very good fit, but it's positive. So it's showing a positive trend there. So what that's saying is as the population density increases, so does the crime rate, which tends to make sense. Now, all they did in the second graph is they took this 1 point out. They omitted that. When they omitted that, it allowed them to stretch out their axis a lot more. They didn't have to count up so high, so it allowed the points to get a lot more spread out. When they did that, when they removed that 1 point, that outlier, look what happened to the line. The line actually went from an increasing line to a decreasing line. It's still not a very good fit because there's a lot of scatter within those points. They're not very closely bunched, but it turned negative. So by adding or removing that single outlier point, it changed the correlation from a positive correlation to a negative one. So with DC removed, what we actually see is as the population density goes up, the crime rate actually tends to go down, very slightly, but it tends downward. When something like that happens, if you have a outlier, a point, whose presence or absence has a large effect on your conclusion, that's then called what we call an influential point. So an outlier may or may not be an influential point. You have to determine whether it's affecting your conclusion drastically or not. So that's a little bit of a personal opinion. Do we think it changed it drastically? Well, I think anytime it goes from one sign to the other, from positive to negative or negative to positive, definitely that's a drastic change. Other than that, it's up to you whether you think that it has changed it enough to be labeled drastic or not, and enough to be labeled an influential point. But definitely you should, when you have an outlier, you should try your regression with and without it and see what happens and see if that point is influential or not. Okay, the other main point we want to make in this video is about extrapolation. Okay, so what is this extrapolation? Extrapolation is making predictions using your regression line outside of the range of data that you have. When you do this, it's dangerous. Because although the association may have a linear shape for the range you're observing, that might not be true over a larger range. Your predictions might be wrong outside of the range. Oops, sorry. Let me try that again. Of the observed x values. So it says, notice that the regression lines in our notes all stop at the lowest and the highest data points. So if we go back and look, we only have 2 in this note packet. But notice this regression line starts here and ends here. It's not like a normal line from algebra class that has like arrows in both directions. So what we're saying is this does not necessarily make sense beyond what we know. We don't put the arrows on the ends because out here I have no idea what's happening. This might continue in this fashion. It might do this. It might do this. I have absolutely no idea what's going on out here. So when you make predictions way out here, outside of the data that you know, that's called extrapolating, and that is dangerous. Okay, so that's why we don't do extrapolation. Okay, last idea is what we call the coefficient of determination. What that is that's the correlation coefficient squared. So you take that R value that you get and you square it. Usually these are converted to percentages. So when you talk about an R squared value, usually you give it back as a percent. Because R is between -1 and 1, if you square those, then your R squared value will end up between 0 and 1. Or between 0% and 100% if you give it back as a percentage. If you get an R squared value of 100%, that means your relationship is perfectly linear. And the regression equation perfectly predicts the observations. A value of 0% means there is no linear relationship, and the line does a very poor job at predicting. Whenever we write up, like, what does this mean? What does that R squared value? The sentence that we use for that says, R squared, whatever that number is, that many percent of the variation in Y values is explained by the X value. So let's go back to the example that we did, the flight times example from section 4.3. As a reminder, we've already seen this. This is a snapshot of what StatCrunch gave us. And we've talked about the regression equation and we've talked about the correlation coefficient. So now notice there's this other value right here. It's always been there, but we just haven't talked about it yet. All this value is this number right here squared. So StatCrunch gives it to you. What is the coefficient of determination for this? There it is. Now, what does it mean? So I need to give it back as a percent. So what it means is that, let's say 98.9% of the variation in flight times is explained by the distance traveled. The rest of the variation in flight times is due to something other than the distance traveled. So let's just brainstorm. What other variables might influence flight times? So yes, a majority of your flight time is explained by how far you have to go. But there are other things. It looks like there's 1.1% of other things that can affect how long your flight is. So I think back to flights that I've been on. Weather, right? If it's poor weather, if it's raining or snowing, that could cause your flight to take longer than it otherwise would. Headwind or tailwind. Sometimes if the wind is blowing with you, you actually will make better time. And if it's against you, it'll slow you down a little bit. I've been on some flights where we had some unruly passengers. Passengers who just couldn't find their seat, couldn't figure out what to do with their carry-on, things like that. That adds to your flight time because you're on the plane, you've loaded, and you're not able to take off yet. So that adds to some of that kind of upfront time where your distance might be 0, but you've still got time associated with that. So overall, though, what we want to get out of this is that's what that R squared value tells you. It tells you that much percent of your variation is